All right, Stephen, this is definitely a both boards kind of day. All right, so couple things. Happy Monday. We've got this one, and next Monday before Thanksgiving break, and then you get to gobble till you wobble. It's going to be a good thing. In terms of your calculus life, today is the day that life changes for you completely. Today is the day that we actually do the work that Riemann did, which is really where he gets like all the recognition and the accolades from. It's not just from this idea of like a little number of rectangles or trapezoids. Like so far we've been dealing with like 4 rectangles to approximate an area, maybe 7 trapezoids. Like that was pretty big for us. Today we get to generalize the process so that you can actually handle an infinite number of rectangles. This is where he got all the recognition and the accolades from that he deserves. God rest his soul. Okay. We're going in deep today, so I'm really excited about all this. Yes, so there is that. Is anyone interested in making corrections to this amusement park problem? Okay. For those of you that are interested in making corrections to the amusement park problem, here's what I'm going to offer, but you're going to make sure that you hear this. Because if you think you'll hear something else, it's not going to work. Get it in my mailbox first thing tomorrow morning. When I get here, I will get it. I will make sure that everything is good. I will adjust the grade in your grade book because that, in my grade book, it's my grade book, not yours. This is the last grade for the second 6 weeks, and for some of you guys the score is a little bit lower than I was expecting it to be, and it counts for 2 homework assignment grades. So if you want it to be a better grade, make the corrections, leave it in my mailbox tomorrow morning. If you bring it in to me, you hand it to me in class, and you're like, hey coach, here it is. I'll be like, you can keep it because it's too late. Pretty good? Alright, so there's that. Tonight's homework. Here's tonight's homework. Tonight's homework is in the student packet, not the problem set packet. So you want to make sure that you write this down. Okay, if you could find lesson 71 in the student packet. Okay, it should be, I think, yeah, flip backwards. It's called the swimming pool problem. There's a great big graph. Starts on page 13. It's pages 13. 14 and 15 is not actually nearly as long as it looks. It's more practice with Riemann sums. Alright, it looks like a lot. For the AB students, they actually would have done that as a lesson in class before hitting the amusement park problem. With you guys, it's a different schedule and I need to move things around. So what they would have done in class for practice, you guys are just going to do tonight for homework, because what we're going to do in class today is not something I want to give you homework on. Got it. I'm going to blow your minds. If we're lucky, Lewis, we're going to get through 1 problem in the next 48 minutes. What? Yeah, no, for real. For real. Yeah, Okay, so the homework that you guys did this weekend, properties of definite integrals. Yeah. Okay, here come the answers. If you could just tear it out carefully. You know what? Don't even tear it out. Don't even tear it out. All you're going to need to do is write down your score on a Post-it note. Okay? So you can mark it up. If you get something wrong, circle it the right answer. Number 1. You could also do like 1 Post-it note for the whole group, or you could burn through all my Post-it notes. Andrew? Yep. Okay, number 1 is B. Number 2 is K. Number 3 is C. Number 4 is G. Number 5 is D. Number 6 is F. Lewis is so stressed he's throwing his calculator on the floor now. 7 is C. 8 is J. 9 C. 10 G. And 11 A. Anybody get 11 out of 11? Nice. How about 9 out of 11 or better? What? 3 was C. Yes, I got 10. Okay, so on the Post-it note or the index card, if you could just write your name and then how many did you get right out of the 11. I'm just going to put that in my grade book, and this will be the first grade of the new 6 weeks. All right. Colin, can I get you to go to the back and you're going to drive? All right. I missed Celeste.
I do too.
There's no one to keep Aaron on his toes. Oh, all right, and we need to do function F8. I already took attendance. Function F8. Don't mess with me, laptop. I just need you to project. Didn't we deal with this nonsense last week? All right, there's that. And we're coming around from the back. There it is. All right, that should work. All right, so here it comes. Perfect. So just click the duplicate and we're out of there. All right, so up until this point, whenever we've talked about Riemann and Riemann's method, there's 4 methods that we talk about, right? What are the methods? We've got the midpoint method, the right endpoint method, the left endpoint method, and the trapezoid method. And what Riemann's method is, the goal is like, hey, here's some function, and you don't have to like jot any of this down, but you do need to focus. We've got some particular function, we've got some interval. So here's my interval from A to B. What I want to do is I want to find the area bounded by the curve, the x-axis, from A to B. We're good? Let's get some answers. What does Riemann tell you to do? What was his idea? If you were going to explain this to an 8th grader. Seriously, like if you wanted to explain to an 8th grader how we go about finding that area, that bounded area, what would you tell them? I don't know if you remember me. Palimon, what would you tell them?
We're just filling in, say, a circular pattern.
Well, it's not even a circle, it's just some curve, right? What do we do in calculus? How do we find that area? You use rectangles to get the exact area? To get close, right? So what you do, fancy words that I'm looking for here, you're going to take this interval from A to B and we're going to do something. We're going to chop it up. Partition, right? You're going to cut it up. Now, you could cut this up any way that you want to. So far, what we've done again and again and again, I kept calling it a uniform partition. You guys remember the word? Uniform partition just means chop it up into equal length pieces. The benefit of the equal length pieces is that when we get to the area, you can factor that equal length out. Everybody okay? And so if I said, hey, let's do 1, 2, 3, 4, and I'm doing this method here. You guys know what this method is.
Right.
This is the right endpoint method, and all my rectangles are leaning in all sorts of ways. Looks like somebody with bad teeth. Right endpoint method, underestimate, overestimate, can't tell.
Over.
Clearly an overestimate. Lewis, why is this giving me an overestimate for sure?
Area levels.
There's area
Above.
there's area above the curve that I'm calculating here that I'm not interested in, right? All I want is the shaded piece. I'm capturing more area than I want, so this is an overestimate. Now, one of the mistakes people make at this point in the game, they think the right endpoint method is always going to give you an overestimate.
No.
Why is that wrong? Why is that wrong, Stephen?
Because if the graph was actually like going concave down.
If the graph was, in fact, it doesn't even have to be concave down. If the graph was decreasing, the right endpoint method, think about a decreasing graph. What happens with the right endpoint method? Now you're going to get an underestimate, right? So it's a combination of like behavior of function and method that says overestimate, underestimate, so on and so on. Everybody's good? This was Riemann's opening idea. And we know that it gives us an overestimate. It's a pretty good overestimate. How do I make it better? Andrew, how do I make this estimate better?
By making more rectangles.
More rectangles. Palamon, show me more rectangles. So let's do show right rectangles.
Oh,
Show right rectangles.
I'm saying more rectangles. I assume you.
Show right rectangles. Okay, and do the n+1 nonstop. Show n+1 nonstop.
It's not showing the blue.
Yeah, we're not seeing right rectangles, are we? Okay, let's
I
click that.
see it over here.
No, you see it,
Yeah,
but
he sees
you're
it.
not showing it up over here? Oh, okay. So hide right rectangles. Sorry, I think we're having some, so click on hide right rectangles so we stop seeing them. Okay? And click on show left rectangles. Okay, you guys can maybe see that a little bit better. Alright, so we've switched methods so that you guys can see, alright? And is everybody okay? We're getting a better estimate?
Yes.
A much better estimate. The left sum says 6.783, 6.789. The true area is supposed to be 6.910. How am I going to get the best estimate possible, though? How do I move from past estimate to exact? You're in a calculus class. How would you move from an approximation of the area to the exact area? How many rectangles would you want?
Infinite.
100.
100. Even at 100 rectangles, and we're closing in on 100, there's going to be a difference between your approximation and what the actual area is. 100 would be good, and it doesn't even let you go all the way out to 100. It stops at like 80 something or other. 100 is good. Better than 100?
Infinity.
1,000 would be better. Better than 1,000? 1,000,000, right? Like God help you if I say like go home tonight and do the estimate with 1,000,000 rectangles. Nobody wants to do that. Lewis is blessing himself like God, please. Don't let him get that idea.
That would happen.
That's not what Riemann did. That's not what he was interested in. What he was interested in was the exact area. Stephen, what was your idea to get to the exact area?
Infinity.
You use an infinite number of rectangles. So if you think about taking your interval from A to B and partitioning that into an infinite number of rectangles, how big is each rectangle going to be? How wide is each rectangle going to be?
Very, 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 very.
It's going to be like dust, right? It's just going to be like this teeny tiny microscopic thing that you can't even measure, and you find the area, and then you add it to the next one, and the next one, and the next one. This is the big idea. Everybody okay? All right, so let's give you guys a little bit of practice. Palamon, you've done a great job. What I want you guys to do is parts A and part B. This is just going to be some calculator practice, and then I'm really going to push your thinking. So Palamon, you can come on back to the world. Give you guys about 5 minutes on A and B. I'm interested in your setup. Get some new calculator skills to share with you guys. What are you guys getting for there's going to come a time where you'll be able to come up with the exact area without the calculator. That is not the goal for this unit, but that's coming. All right, A and B. What'd you get for the exact area? Did you get the exact area? Yeah. No. Sorry. Where we are here. Sorry.
That's all the big ideas from
Yeah, this is where we are. So we get an exact area. And it could be, but I'm really interested in what you do on part B. Good. Now keep in mind, you can do the definite integral through on like the calculate screen, or you can do it on graphing. But I'm really interested to see what you guys can do with part B.
But in by 20. 0 to 3.
Alright, so for part A, everybody has 39 as their area? Okay, good. As I was sharing with the friends in the back, there will come a time where you will have the skills necessary to find that area without your calculator. Not 8 over 3. 3 over 8. Right, because you're going from 0 to 3. So you lost that argument with friends, huh? Okay. Yeah, so we're going from 0 to 3. And so when you're evaluating a definite integral, it's bounded by 4. The x-axis has to be 1 times. So it's going to have to be everything below the curve but above the x-axis. Yep. Otherwise, this isn't bounded. That area would go on forever.
F1 yeah, 3 It's 2.7. Keep the height. I'm doing a fraction and add all these together.
Wait, are you?
All right, friends, let's pull this together. So I want to find the area from 0. Ooh, that's a noise for a Monday morning. From 0 to 3. You need to pay attention to the method and the number of things that you've got. We're going to go from 0 to 3, and I want 8 rectangles of equal width. I could have used the phrase uniform partition here if I wanted to. And I want the right endpoint method. So if I'm going to use the right endpoint method, I need to know how wide is each rectangle. Right? Usually to figure out the width, we're going to say, like, let's find out how long the interval is and divide it by 8. I'm just going to say with the fraction 3 over 8. We're okay? All right, let's look at the partition. If I'm going from 0 to 3, what are the partition points? If each rectangle has a width of 3/8, the first rectangle starts at 0 and ends at 3/8. The next one goes from 3/8 over to, I'm going to leave it as 6/8 for a reason you'll see in a bit. The next one goes 6/8 to 9/8, 9/8 to 12/8, 12/8 to 15/8, 15/8 to 18/8, 18/8 to 21/8. The last one, 21/8 to 24/8. 24/8, that's a good thing. That's 3. Everybody good with the partition? All right, so your first rectangle, if we're going to go with the right endpoint method, Lewis, tell me if we're going to approximate this guy over here. Tell me about that first rectangle. How wide, how tall?
It's 3/8.
It's 3/8 wide. How tall?
F of 3.
F of 3/8, right? Whatever this right endpoint is here, I know I go over to 3/8, up, over, down. F of 3/8. David, tell me about the second rectangle. How wide, how tall?
Wide is 3/8.
Wide is 3/8. How tall?
And F of 3/8.
F of 6/8. Giselle, tell me about the third rectangle. F of 9/8, because for every one of these intervals, I'm picking the point on the right to plug into the function, okay? All right, and I bet you guys we can do this quickly. Next, 3/8 times f of 12/8. 3/8 times f of 15/8. 3/8 times f of 18/8. 3/8 f of 21/8. 3/8 times f of 24/8. Like, that's what I would need to see written down to say, oh, you know what you're doing. Is everybody okay? Ways you can make this a little bit better for yourselves include that 3/8 is a common factor, right? That would be good. That would make my life better. I'm going to have 3/8 times f of 3/8, f of 6/8, and da-da-da-da-da-da-da-da, all the way out to f of 24/8. I'll tell you what the final decimal number is. According to my calculations, I think that this is approximately 44.765. Did anybody actually get to the computation part? Aaron, it looked like you had a question earlier. Okay. Big picture, is everybody okay? Friends up front, we're okay? Really time consuming to type this into the calculator. Riemann had no calculator. Riemann had other ideas. So let's push the thinking a little bit more, and I think this next one is really going to catch you by surprise, but it's going to be okay. What I want to do is see if we can unlock the pattern here. What I want to do is, rather than monkey around with 8 rectangles, I want to generalize this to n rectangles, where n could be any number that you want it to be. Like, this is the power of mathematics. So write endpoint method, n rectangles, create an expression which can be used to determine to estimate the value there. N rectangles of equal width. I'm going to go from 0 all the way out to 3. I made this a little bit bigger so I could have more space to play around with. My first question, how wide is each rectangle? How wide is each rectangle going to be? Aaron, how wide is each rectangle going to be? Right, the width of each rectangle, so that width, which I like to call delta x, is 3 minus 0 over n, 3 over n. I'm going to partition my interval. Let's talk about those cut points. The first rectangle starts at 0 and ends where? Not at 3. Not my first rectangle. It's going to end at 3 divided by n. The second rectangle starts at 3 over n, and you move 3 over n spaces to the right, and where do you land? 6 over n. The next rectangle? 9 over n. 12 over n.
The same thing, you're just replacing the 8 with n.
And when you get to the last one, you're going to have 3n over n, which is 3. You're using the right endpoint method all the time. I'm doing a much better job. My teeth are getting better. Okay, 1, 2, 3, 4, 5, all the way out to the nth rectangle. Everybody okay with the partition? We're good? All right, so let's come up with a way to represent it this time. The integral from 0 to 3 of f of x dx is approximately, Myra, tell me about this first rectangle. How wide, how tall?
Wide, 3 over n.
Wide, 3 over n. How tall?
F of 3 over n.
F of 3 over n. That's the first one. Palamon, tell me about that second rectangle. How wide, how tall?
6 over n.
Is 6 over n the width?
No, it's 3 over n.
3 over n is the width. How tall?
6 over n.
F of 6 over n. That's the second one. Ilay, tell me about the third one.
The width is 3 over n.
3 over n, and how tall?
F of 9 over n.
F of 9 over n. And Giselle, what about that fourth rectangle? How wide, how tall?
3 over n.
3 over n.
Times 12 over n.
F of 12 over n. We're okay? And we're going to keep on going. Andrew, tell me about that last rectangle, this nth rectangle. How wide, how tall?
3 over n.
3 over n.
F 3.
f of 3, which I'm going to write as f of 3n over n, if everybody's okay with that? Okay, I don't know that I gave you guys enough space to write here, but we're going to keep on going. Is everybody okay with the setup? I want clever mathematics that's going to make your life better. That would make your computation life better. Take out that 3 over n, right? This is why we do so much work with uniform width. I want that width to be the same so that I can do something way clever. F of 3 over n, f of 6 over n, f of 9 over n, all the way out to f of 3n over n. Okay? N could be 1,000, and I'd have 1,000 of these little guys here. It could be 1,000,000, 1,000,000,000, anything I want it to be. Here's the thing that you're not going to see coming. I want to find a better way to write this. There's a pattern here. F of 3 over n, f of 6 over n, f of 9 over n, f of 3n over n. What do you think of how much?
Just put 3 plus 6 plus 8 over n.
3 plus 6 plus 9?
You're saying put it all over, like add the numerators up and all over.
But here's the problem. 3 over n is what I plug into f, and I evaluate f at 3 over n. So that means I can't just combine 3 over n, 6 over n, 9 over n. This next thing you're not going to see coming. What I'm going to do, all these guys are being added together, right?
Yep.
I have a notation, a super secret notation that you haven't seen in a very long time that represents adding up. When there's a pattern, it's so good. It's even built into your sigma notation. Sigma notation is going to allow me to collapse all of this down. Okay. Stay with me here. Sigma means add. Okay? In AP Physics, you did it all the time. You were summing forces. In pre-calc, we did a little bit of it, but not nearly enough. Okay, with sigma notation, you always have a starting value and an ending value. I'm gonna use K as my counter, K for Keith. And the College Board uses K all the time now. Carmen's like, that was so dumb. The College Board uses K all the time. Now, there's a pattern here, isn't there?
Yeah.
It's f of stuff being divided by n. The pattern, 3, 6, 9, the next one would be 15, 18. How am I going to write that pattern in the numerator? If my counter is k, I can write this as 3k over n. If k is equal to 1, do I get this guy over here?
Yes.
If k is equal to 1, this is f of 3 over n, check. If k is equal to 2, because the counter increases by 1, 3 times 2, 6 over n. K is equal to 3 now. 3 times 3 over n, 9 over n. Good. And so on and so on and so on. Where does my counting stop?
3.
This is the first one, the second one, the third one. When do I stop?
3.
It's not at 3. N. Because I have n
Oh, because
rectangles.
you plug in the n, once you get that, it'll make 3n over n.
Right. This is your starting value. This is your final value, f of 3k over n. Okay? Now, the thing that's in black represents all this fun stuff. I still have to multiply by 3 over n. This is going to be how I approximate the value of the definite integral of my function from 0 to 3. We're going to play around with this today. We're going to play around with it tomorrow. And quite honestly, like, getting here is big. Getting past this is going to be tricky. So I've got some new calculator skills that I want to show to you guys. Okay, so I'm just going to write this on the side. K goes from 1 to n, f of 3k over n. All right. David, do me a favor. Can you erase the board? I'm going to go to the back and I'm going to drive.
You want all the one on the right?
The stuff on the right. All righty, friends. So here's what we're going to do. Oh, sorry, I forgot to switch my source. Sorry, you're good where you are.
What?
All right, back over there. On the calculator. If you haven't done so yet, on your graph, please make sure on your graphing screen you typed in the function. Aaron, what was the function that we're dealing with here?
F of x equals 2x squared
2x squared
plus 4x plus 1.
plus 4x plus 1.
Yes.
On your calculate screen, we're going to do menu. Oh, yep. Okay, so on my menu, now I'm not looking for the integral. Menu, calculus, sum. Look at that. It's all there. All we're going to do is fill in the blanks. Now here's what I want to be careful with. We've already done this problem once. We've estimated using 8 rectangles. So let's do the setup for 8 rectangles here. If we're going to use 8 rectangles up here, I want to make sure you can get this typed into your calculator. In front, 3 divided by 8. I want to use my mouse to like point to the thing in like that top left. Right, n is the number of rectangles, so in this case n is 8. My counter, give it a letter. I'm going to say k goes from 1. When do I stop summing? At the 8th rectangle. And now what am I summing? I'm summing f1, which is why I needed to put that function in there. Parentheses. Now I need to evaluate f1 at, and here's where you need to be careful, 3k divided by n, but what's n in this problem? 3k divided by 8. Hit enter. And your calculator gives us this beautiful answer of 2,865 over 64. If you change that to a decimal, Control Enter, 44.7656, which is exactly what I gave you guys earlier. Everybody mostly okay? Please keep in mind, Riemann didn't have this tool. He grew up in the 1860s. They didn't have the TI Inspire or the TI-1. I don't even think they had electricity. Okay, here's what I want you to do. I want you to get a little bit of practice with your newfound skills. So do E, F, and G. In E, you're going to come up with an approximation using 120 rectangles. In F, you're going to use an approximation using 1,000. In G, you're going to get an approximation using 10,000 rectangles. Have a quick conversation with the folks around you. What are you expecting to happen? Don't tell me, tell the folks around you. What are you expecting is going to happen as you go from 120 to 1,000 to 10,000 rectangles? What are you guys expecting over here? With 8 rectangles, we're getting an approximation of 44.765, right? 120 rectangles. Smaller than that, but there's more rectangles. Why smaller? You're getting a closer estimate. So it should be a smaller number than 44.765. Small, like close to 0, or small, like close to something else. Closer to what the true area is. And the true area, you just looked it up. What's the true area? 39. You should be getting smaller. You should be getting more precise with your estimate, closer to 39 as you go. Yeah, definitely I want to like show the setup. And keep in mind, because your calculator's going to do all the work here, nobody needs you to simplify.
Oh no, I just put one over.
Right, I mean, there's nothing wrong with that. Yeah.
that.
And the reason why I didn't simplify earlier when we were doing like the cut points is that like if you went like 3/8, 3/4, 9/8, the pattern's not as clear as if you're like 3/8, 6/8, 9/8, 12/8.
Sometimes of the problem.
Yeah. Andrew, is the first one 120 rectangles?
Yes.
So I'm going to do something way clever here. I'm just going to do my little copy paste feature. So 3 divided by 120. And I deliberately made a mistake.
You left the 8 on top, man.
Right, I left the 8 on top. You've got to change everything to being about 8. So 3 over 120 is the width, or as Aaron has it, 1 over 140.
No.
Summing from 1, you had 1 over 40, right? Summing from 1 to 120, F1 of 3k over 120 is 6301 over 1600, and if I do control approximate, 39.375? Are all the friends okay with 39.375? Okay. Right, and what was the next one, 1,000?
Yes.
Okay, 3 divided by 1,000. Alright. Control enter 39.045. Can I get some confirmation from friends? Are we getting 39.045?
Yes.
Okay, now, I know you guys know this. As you get more rectangles, your estimate gets better. It gets more precise. So now I'm at 39.0045. 39.0, because now we're on the last one, which was 10,000 rectangles. Now, we are not going to do something stupid here. We're not going to try putting in an infinite number of rectangles. Your calculator can't handle that. That also isn't the path that Riemann went down. Here's what I care about though. Is everybody okay with the setup? Like, you kind of see where the pattern's coming from? Sigma notation is definitely a leap into a place where you may not have been expecting. But here's the thing. Even if you went out to 1,000,000 rectangles, is that the exact area? It's still an approximation, Stephen.
Isn't there a formula for infinite sum?
What?
Isn't there a formula for infinite sum?
There's all manner of stuff coming, Stephen. And honestly, like if we're coming up on the end of what we would do in an AB class. You guys can put the calculators away because this is not what Riemann did. It's close. It's close. Aaron, you okay with that?
No. My calculator couldn't handle the number.
Yeah, I carefully picked the value so that you wouldn't overflow your calculator. Alright, so if what I wanted to do, and I'm gonna introduce my notation this way. If what I want to do is approximate the integral from 0 to 3 of f of x dx using, I'm going to call it a of n, where this is going to represent area using n rectangles of equal width, and we're using the right endpoint method, then the setup is the width of each rectangle is 3 over n, right? We're doing a sum from where to where?
Okay, good one.
From k equals 1 to where?
N.
To n. And it's f of 3k over n. Everybody okay?
Yes.
Now, some textbooks are going to do this. They're going to say, take this 3 over n and bring it inside the summation. Remember, like we factored out that 3 over n in the beginning? You didn't have to. Some textbooks are going to write it this way. They're going to say 1 big sigma, and then they'll put the 3 over n times f of 3k over n like that. It's okay, it's legal, there's no reason to not do it. It's totally okay to do that because what's changing in this problem is k. K is 1, then it's 2, then it's 3. 3 is a constant. N is a constant. You determine the number of rectangles in the beginning and it doesn't change. So having that 3 over n out front or multiplying it through is going to be okay. But this is still an approximate or the exact answer? This is still an approximate. How do I get to the exact answer? How do I get to replace the approximate symbol with an equal to sign? How many rectangles? An infinite number of rectangles. So what we need to do is look at the limit as n approaches infinity of this sum from k equals 1 to n, 3 over n, f of 3k over n. If you can evaluate the infinite case, that's what's going to give you the equality over here. It's no longer an approximation, it's an exact answer. And yeah, don't worry about that. And for the friends that are in Calculus AB, this is where we would stop. We would just stop here. We'd say, like, we're here.
Good thing we're BC, guys.
Good news, we're in Calculus BC. Because here's the thing, Riemann didn't stop here. Riemann kept going. Because Riemann was amazeballs. So this is what Riemann did, and Stephen, can you see me if I'm over here?
Yes.
Okay. Here's where we're going to run into a little bit of a challenge. There are some gaps in your pre-calculus knowledge that I'm just going to have to push past right now. There are these shortcut formulas for working with sigma notation that you can look up on Google. Stephen's probably already done that, or he's doing it right now. These are ways to sum up these expressions in really nifty ways. I know I'm going to go a little bit too fast here, just stay with me. Okay, we've established that the integral from 0 to 3 is found by doing the limit as n approaches infinity. The sum k goes from 1 to n, 3 over n, and we're going to evaluate f at 3k over n. I know I'm going to go fast, so just try to keep up. The original function was it 2x squared plus 4x plus 3?
Plus 1.
Plus 1, thank you. What I'm going to do is I'm going to replace f of 3k over n, but I'm going to go over to f of x, and everywhere there was an x, plug in 3k over n. What that means is that my sum here, we're going to go k is 1 to n, 3 over n, big brackets, 2 times x squared. Well, x is 3k over n, square that, plus 4 times x, plus 1. What I'm doing here is replacing this generic f of 3k over n with what would happen if I plugged 3k over n into my specific function. Everybody kind of okay with what's happening? I still need to take this limit as n approaches infinity. Well, let's keep going. I'm going to take the limit as n approaches infinity of this sum. This next move, we're going to do as much algebra as we can here. Just kind algebra. 3k over n, if I square that, 3k over n times 3k over n is 9k squared over n squared. But that's not the end of what I need to do here. I need to multiply by 2. So that gets me to what, 18k squared over n squared? And then I've got this 3 over n that's going to get distributed all the way through. It should be 54, that was what, 9k squared over n squared, 18k squared over n squared, 54k squared over n cubed, plus 4 times 3k over n is 12k over n. 3k over n multiplies that as well. We're going to get 36k over n squared. Plus 3 over n times 1 is just 3 over n. I'm not going to take any questions on this because I'm really not too worried about you keeping up with the algebra here. One of the properties of sigma notation is that if I'm finding a sum of all 3 of these things, it is the same. It is legal to say, take the sum of this first term, take the sum on the second, take the sum on the next one. What's going to happen is your expression is limit as n approaches infinity of the sum, k goes from 1 to n, of 54k squared over n cubed, plus the sum, k goes from 1 to n, 36k over n squared, plus the sum, 3 over n. All I did is I distributed the sigma to each of these terms. I'm going to add them up differently, and that's okay. Everybody still kind of with me? All right. Now, with sigma notation, what's changing is the k value. Everything else is constant. K is 1, then it's 2, then it's 3, then it's 4, all the way out to n. So in this sum, what's a constant?
What's a constant?
What's a constant in this part over here, in this expression? 54 is clearly a constant. And n is a constant. With sigma notation, think about you're summing up a whole bunch of terms that are like 54 times 1 squared over n cubed, 54 times 2 squared over n cubed, 54 times 3 squared over n cubed. The 54 and the n cubed are constants that you can factor out in front. We're going to get the limit as n approaches infinity of 54 over n cubed, the sum, k goes from 1 to n of k squared, plus, over here the constants, 36 and n squared, pull them out in front. If this was something that we did in pre-calculus, you guys would be much more comfortable than you probably are right now. Okay? The 3 over here, the n, those are constants. I pull them out in front. Plus 3 over n. The sum goes from 1 to n of just 1. Here comes the last thing involving sigma notation. This sum here says sum from 1 to n over k squared. That means find 1 squared, plus 2 squared, plus 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, until you get to n squared. If this was something we had covered in pre-calculus, you guys would know that it's actually this sum over here, right? And rather than k, I was using I in this problem, can be found by doing this. This is it n? N plus 1, 2n plus 1 over 6?
Yeah.
Okay. Still multiplying by the 54 over n cubed. I promise, nothing that's over here is what I'm going to be assessing you guys on. I just want you to be there for the whole conversation. Okay, plus 36 over n squared. I think there's a formula over there that tells you how to sum from 1 to n. 1 plus 2 plus 3 plus 4 plus 5. What is this formula that you don't know from pre-calculus, but it's on the paper? What does it tell you to do? It's n. N plus 1 over 2 plus this last one. You're summing from 1 to n the number 1. 1 plus 1 plus 1 plus 1 plus 1 n times is n. We are so close. The only thing standing between you guys and fully being on Riemann's path is evaluating that limit. Anybody see any legal math that you could do that would make life maybe a little bit nicer? There's no more sigma notation. There's no more sigma notation property showing up. I just want to know what's the limit as n approaches infinity of all this stuff over here. I'll take anything from anybody on any part. It's all algebra. Okay. 3 over n times n.
Cancel out.
Cancel out the n's. Left with 3. 36 over n squared times
Oh.
n times n plus 1 over 2.
Cancel out the n squared.
That little n down there and that little n up there cancel out. The 2 and the 18, 2 and the 36 can be reduced to 18. What's the limit as n approaches infinity of 18 times n plus 1 over n?
Wait, so
Degree 1 in the numerator? Degree 1 in the denominator? What's that limit? This is 18. How about over here? Degree in the numerator? Well, let me back up on that thought. 6 in the denominator, 54 in the numerator, I can reduce if I wanted to. I've got an n up here and an n down there, makes that n squared. 9 n plus 1 times 2n plus 1. If you were to multiply that out, that's going to be degree 2. The leading coefficient is 18. In the denominator, the leading coefficient is 1. What survived from all of this is 18 for this first part, and 18 for the second part, and a 3 for the last part. 18 plus 18 plus 3?
39.
39. What's the exact area bounded by that curve on the interval 0 to 3? 39. Insert thunderous applause here.
I got that number.
Or, thank you, Mr. Lincoln. Woo! I did it! I got to 39! Okay, so tonight's homework, I just want you to do this like 7 more times.
What?
Or do the swimming pool problem, Scooby.
I don't know.
What did you do?
I don't know.
That whole last part you will never be assessed on, but it's not a complete BC experience unless you go through it at least a couple of times. Don't be absent tomorrow. Good luck, Celeste.
One of I'll go
What I eat?